So if you have your quadratic function in the form ax squared plus bx plus c, where a, b, and c are real numbers, a is not 0, because if a was 0, we wouldn't have a quadratic function. How do we find the vertex? So it can be shown by completing the square, which we won't do in this video. But if you complete the square on this function, it can be shown that the function is actually equal to a times x minus negative b over 2a all squared plus c minus b squared over 4a. Now let's compare that with a times x minus h squared plus k. Remember, hk were the vertex. hk were the vertex. So in other words, if we take out this piece here, that's my h. So negative b over 2a is going to be the h. And k is going to be c minus b squared over 4a. This entire piece is c minus b squared over 4a. So that is the actual vertex of the function if you're given the function in ax squared plus bx plus c form. So you know a, b, and c because those are the coefficients here. You just plug them into this formula, you find the vertex. But even more simple is this second piece here is not necessary. We'll use it one time, but you can actually find the vertex by doing negative b over 2a. And remember, this is a function. This is the x-coordinate of my vertex. So to find the y-coordinate of my vertex, just plug that in to the function. So f of negative b over 2a gives me my y-coordinate of the vertex. Remember, this is the x-coordinate, this is a y-coordinate. So by plugging in the x-coordinate of the vertex into my function, we can find the y-coordinate. So let's take an example. So suppose we're given a function, f of x, a quadratic function. F of x is negative 3x squared plus 6x minus 13. It says find the vertex, the coordinates of the vertex. The vertex is a point. It's either going to be the highest point or lowest point. So from our formula here, if we're given a function in this form, ax squared plus bx plus c, the x-coordinate is at negative b over 2a. Let's just list that here. A is negative 3, b is 6, and c is negative 13. A is negative 3, b is 6, c is negative 13. So negative b over 2a, what's that going to be? Well, that's going to be negative 6 over 2 times negative 3, negative b over 2a, and we calculate that, negative 6 over negative 6 is 1. So that's my x-coordinate, Now we want the y-coordinate. We could either use this formula or this one. We're going to do both, just to show that they're the same. So c minus b squared over 4a. And if we plug in those values of c, b, and a into the formula, we get negative 13 minus b squared, 6 squared, divided by 4 times a, 4 times negative 3. So we simplify this and we get, so negative 13 minus 6 squared over negative 12, 36 over negative 12 is negative 3, so we'll have a minus minus 3. But negative 13 plus 3 gives you negative 10. So that's the y-coordinate. So therefore my vertex is at 1, negative 10. Now we said we would do it the second way, so if we do it the other way, if I plugged in 1 into my function, we would have negative 3 times 1 plus 6 times 1 minus 13. And if we calculate that out, well, that's negative 3 plus 6 is 3. 3 minus 13 is negative 10. So we get the same y-coordinate. So either you use the formula or you plug the x-coordinate back into the function. It gives you the y-coordinate of the vertex. So now let's sketch a graph of this function. So here we have the xy coordinate plane. I'm going to graph the function negative 3x squared plus 6x minus 13. We determined the vertex is 1, negative 10. 1, negative 10 is approximately here. And what else do you need to graph it? Well, a y-intercept would be good. Well, the y-intercept comes from f of 0. And if I plug 0 into the function here, what's nice in this form is if you plug 0, all of these x's drop out, and we end up with just negative 13. So my y-intercept is right at negative 13. That's where it hits the y-axis. Does it open up or does it open down? It opens down in this case because a is negative. A is negative 3, and it's negative. So it's going to open down. So if we finish this sketch, we have a graph like this, and it's opening down, my vertex at 1, negative 10. Now, a few things to note from this graph, this particular function here. It's never going to hit the x-axis. So it doesn't have any x-intercepts. Okay, as we'll see as we go on, it does have what we call zeros, but they're imaginary. But this doesn't have any x-intercepts. The second thing is from a graph, once you know the vertex of a quadratic function, it's either the max or the min. So from that, you can always determine the domain and, more importantly, the range of a quadratic function. Now, the domain of a quadratic function, as it's given, is always going to be all reals. You can plug any x value into this quadratic function, and get out a y value. However, the range is restricted by the vertex. We see that it starts here at negative 10 and then goes down. And you don't have any numbers higher than negative 10 in the range of this function. Remember, the range are the y values. So therefore, my range, we could say, is from negative infinity all the way up to negative 10. And use parentheses around infinity because you never reach infinity. So from negative infinity to negative 10 is my range, or if you'd like to say y is less than or equal to negative 10. So these type of quadratic functions lend themselves well to applications because remember, in a quadratic function, the vertex is either the maximum or minimum. So we're going to do some applications of quadratic functions.